Hello everyone, welcome to my class. In today's class, I'm going to cover section 14.7, the maximum and minimum values of the surface. Let me start the class right away. First, quick recall. The landscape of a surface is a little bit complicated to sketch than the profile of a curve. It has peaks, it has hollows, it has valleys and mountain passes. We can visualize on our right side here. There is a surface. It has absolute max. It has a saddle point, means no max and no min in this valley here. We have local max. You have absolute mean somewhere here, and local mean here. Also local mean here. So the first question we used to answer here is how to find the maximum and minimum values of graph of function of two variables. So the key idea is partial derivatives. Let me scroll down. Quick remark, finding the extreme values of f of xy is also called an optimizations. There are two types of optimizations. Unconstrained optimizations we cover in these sections. In the next section we will cover the constrained optimizations. So let's begin the unconstrained optimizations. Next, the definitions of critical points or stationary point. A point AB is called a critical point of f of xy if, condition A, both the partial derivative of f with respect to x and y evaluated at AB equals to 0, or conditions B, one or both partial derivatives of f with respect to x and y and evaluated at AB does not exist. Quick note, if f of xy has a local extrema at point AB, then the point AB is a critical point. However, not all critical points give rise to a local extrema. By the way, if a graph of f has a tangent plane at a local extrema, then the tangent plane must be horizontal. Next definitions, saddle points. A point AB is called a saddle point of f if AB is a critical point, but f has neither a local max nor a local mean at that point AB. Example, think of saddle point is the point on a horse saddle. One can walk upward in one direction and one can walk downwards in another directions. Or for example, the graph I showed earlier in this mountain pass here, we can walk in one direction upward, one can walk another directions downward. So this point has no max and min here. That's why this point is called a saddle point. Let me scroll down again. Another definitions, discriminant of f. The discriminant of f is the 2 by 2 determinant of Hessian matrix. It's denoted and defined by d equals to the partial derivatives determinant here, fxx, fxy, fyx, fyy, and the mixed partial derivatives are equal. Then let's expand this determinant. It gives us fxx times fyy, we multiply this diagonally, and minus we multiply this diagonally, f square or fxy square. Another question, let's ask to ourselves, suppose we found a critical point, then how do we classify that critical point as a local minimum, local maximum, or saddle point? The answer is we need to use SPDT, second partial derivative test, which is our next. So let's move on. So the theorem, second partial derivative test for local extrema. Suppose the gradient of f at AB equals to 0, that is AB is a critical point of f and DAB is the discriminant. Criteria A: if discriminant is positive, then f has a local extrema at the point AB. Then refer part I and II below. Part I, and that subpart I: if the second partial derivatives of f with respect to x evaluated at AB is positive, then f has a local minimum at that point AB, and the minimum value is f of AB. Just looks kind of opposite here. It's a positive here, but we have local minimum. Subpart 2: if the second partial derivatives of f with respect to x evaluated at AB is negative, then f has a local maximum at AB, and the maximum value is f of AB. Part B: if the discriminant is negative, then f has no local extrema at AB, that is AB is a saddle point. Part C: if discriminant is 0, then the test is inconclusive. We cannot conclude whether the graph has a local max or local mean. Great. So I hope this criteria makes sense to you all. Quick remark: in above part A and subpart I and II, the discriminant positive implies fxx and fyy have the same sign, so which then implies that in above cases I and II, we can replace fxx by fyy. Means we can put here fy, we can check here at fyy. Great. So let's move on. Next, let's talk about absolute extrema of f of xy on some closed and bounded region D in R2. One theorem, extreme value theorem: if f is continuous on a closed and bounded region D, then f attains its absolute maximum and absolute minimum value at some point in D. This types of extreme value theorem we also learn in calculus 1, where we define on the closed interval. So if the function is continuous on a closed interval, then f has its absolute max and absolute mean somewhere in that intervals. Let's move on. Next note: the absolute extrema occurs either at critical points, means inside the domain or the region D, or on the boundary of region. And by the way, there are several ways to find the extreme values on the boundary of the domain D, and sometimes harder to find the extreme values on the boundary. Now the ideas: steps to find the absolute extrema of f on the region D. First step: find the critical points of f in the interior of D and evaluate f at those points. Step 2: find the extreme values of the restriction of functions f on the boundary of D. Step 3: compare and conclude that the largest value of f obtained in above steps is the absolute maximum of f on the region D, and the smallest value is the absolute minimum of f on the region D. Great. Last remark before starting the example: to find the shortest distance to a plane from a point, we minimize the square of the distance functions. Great. So let's take some examples. Example first: find the local extrema of functions. F is given by 4x squared plus y squared. It's a paraboloid. It's a familiar surface, which the graph looks like here on my right side here. And from this graph, we see this paraboloid has a local minimum at the origin. Now let's verify this information using our SPDT formula or theorem. So solutions. So first find the critical point. So let's take the first partial derivative with respect to x and y and set those derivatives equals to 0. So here fx is 4 times 2 is 8x. Y square is constant for x partial derivatives. Similarly, fy equals to 2y. Set fx equals to 0 gives us x equals to 0. Set fy equals to 0 gives us y equals to 0. So we have only critical point 0, 0 origin. It makes sense to us from the graph also, right? Awesome. Now let's take second partial derivatives. So fxx 8, fxy so 0. Similarly, fyx 0 and fyy here fyy equals to 2. Then find the discriminant at the critical point. So it is 0, 0 equals to fxx times fyy minus f squared xy. So 8 times 2 minus 0 square equals to 16, which is positive. So then we apply conditions. Let's see here. We apply the conditions part A. We have the discriminant positive, and also our second partial derivative with respect to x is 8 positive. That means we have a local minimum at the critical point, and the local minimum value is f at the origin, right? So that's the next step here. So f has a local minimum at 0, 0, which is f0, 0 gives us the value is 0. So great. So this verifies this graph also, right? I hope it makes sense to you all. Now let's move on. Example 2. Consider the functions f equals to x to the power 4 plus y to the power 4 minus 4xy plus 2, and answer the sub-questions A through C. So first A part, find the critical points of f. What's the idea? Take first partial derivatives of f with respect to x and y, set those equals to 0, solve for x and y. Great. So here find fx, which is 4x cubed minus 4y, set equals to 0. Then we can factor the 4 out, and x cubed minus y equals to 0. Similarly, find fy, which is 4y cubed minus 4x, set equals to 0. Then again we can factor the 4 out, and we can divide both sides by 4, which disappear here. Then we have y cubed minus x equals to 0. We have two equations, two unknown. Let's solve this system. Then from the first equations, put y equals to x cubed in the second equations. Then this gives us x cubed outside cubed equals to x. Then bring this x to the left side. Then we have x9 minus x equals to 0. Factor the x out. Then set equals to 0 by using 0 property. Either x0 or x to the power 8 minus 1 equals to 0. That means x equals to 0 or x equals to plus minus 1. So let's find the corresponding y values. When x is 0, y is 0, because here we use y equals to x cubed. When x is plus minus 1, y is plus minus 1. That means when x is plus 1, y is plus 1. When x is minus 1, y is minus 1. I hope this computation makes sense to you all. Then we have the critical points 0, 0, plus 1, minus 1, minus 1. So we have 3 critical points. Great. Now let's move on. Now another questions. The part B, it says classify the critical points. So let's classify those critical points as a local max or local mean or saddle. So that means we need to use SPDT test. So here, find the second order partial derivatives of f with respect to x and y, and x and y. We have those corresponding values here. Find the discriminant. Discriminant equals to fxx times fyy minus fxy square. Evaluate at the critical point AB. That means we have to check this discriminant and SPDT for each of these 3 points separately. So first let's do for 0, 0. Discriminant is here, fxx at 0 is 0, fyy at 0 is 0, fxy at 0 is -4, so we have 0 times 0 minus 4 square equals to -16, right, which is negative. So discriminant negative implies that 0, 0 critical point is the saddle point. So no max and no min. Next, let's check for point 1, 1. So first find the discriminant. Discriminant equals to fxx at 1 is 12, fyy at 1 is 12, so 12 times 12 is 144 minus fxy is -4 square, so 144 minus 16 is 128, which is positive. Again, here we don't care the value, we only care the sign, whether it's a positive or negative. So discriminant positive, then we need to check the fxx at that point 1, 1. So fxx at 1, 1 is 12, which is positive. That means we have the local minimum at that point 1, 1. Awesome. I hope this makes sense to you all. Move on. Next, for point -1, -1, the discriminant again turns out to be positive, since fxx at -1, -1 is 12, which is positive. We have the local minimum exists again at that point -1, -1. Now let's do another questions. Now find the actual local minimum and maximum values of f. So that means we have to evaluate our functions at those critical points, not at saddle point, but those at 1, 1 and -1, 1, because 0, 0 is the saddle point, right? So local minimums are, since our functions are here, each terms are even terms, so I just put both values 0 plus -1 combined. So f plus -1 plus -1 equal turns out to be 0. So that's our local minimum values. Great. Similarly, let's move on. Example 3. Find and classify all the critical points of these functions e to the power -x square minus y square. So then this question covers part A and B of our earlier example 2. Okay, first we need to find out and we need to classify, but we're not finding actual maximum or minimum values for these questions. So let's begin the solutions. So here, given functions can be rewritten as fxy equals to e to the power -x square times e to the power -y square, because we can combine these functions, which is here. Now take the partial derivatives. Here's fx. Use the chain rule here. It turns out to be this expression, set equals to 0, and then this gives us x equals to 0. Similarly, compute fy. Use chain rule to find the derivatives, but keep in mind when you are taking partial derivatives with respect to y, we are keeping x constant, and in earlier when you are taking partial derivatives with respect to x, we are keeping y constant. Set fy equals to 0, solve, it gives us y equals to 0. By the way, here the exponentials cannot be 0, so only possibility is this term equals to 0, that's why y is 0, similarly x 0. So we have only critical point 0, 0 means origin. Now we found the critical points. So now to find or to classify the critical points as local max or local min or saddle, we have to use SPDT test. That means we need to find out the second derivatives, we need to find out the discriminant and see the sign of the discriminant, right? That's the idea. Okay, so let's find fxx. So here is already we found fx. Use product rule as well as the chain rules. And here is fxy, here is the fyy, here is the fyx. I hope this partial derivatives make sense to you all. Let's find the discriminant at this critical point is 0, 0, which turned out to be 4, which is positive. So discriminant is positive. Then next I need to see the sign of fxx at 0, 0. So it turned out to be negative 2. Then by SPDT, f has a local maximum at the critical point. In the extra, I also computed the actual local maximum, which turned out to be 1. Awesome. I hope this makes sense to you all. Let's move on. Example 4. Now, let's talk about finding the absolute extrema of function of two variables. So the question is, find the absolute extrema of f equals to x squared plus y squared minus 2x on the triangular region T. The triangular region is here, which has vertices 0, 0, 2, 0, and 0, 3. This is bounded by x greater equals to 0, y greater equals to 0, and the line 3x plus 2y less than or equals to 6. See this line. Solutions. So to find the absolute extrema, we have 3 steps. The first step, we need to find out the extreme values of f inside the domain. Now here's our domain. Our region is the triangular region T here. Step 2, we need to find out the extreme values of the restriction of the functions on the boundary here. Our boundary is the union of these 3 lines here, L1, L2, and L3. And step 3, we just compare and conclude. So step first, that means the step A here, find the extreme values of the functions inside the triangular region T. So just the routine computations, find first partial derivative, set equals to 0, solve for x and y, it gives us the origin. So origin is the only critical point of our function, and we evaluate the value at critical point, which turns out to be when x0, y0, we have value 0. So we found the extreme value in the critical point is 0. It means here it's 0. Let me hide that 0 here. Haha. I hope this idea makes sense to you all. Now the next, let's talk about finding the extreme value on the boundary lines. Here the boundary of our triangular region is L1, L2, L3. So let's do separately. Step 2, find the extreme values of the restriction of our functions on the boundary of the triangular region T. So the boundary region contains 3 lines here. One is L1, is a x-axis where y is 0 and x between 0 and 2. Another line is L2, which is y-axis where x is 0 and y between 0 and 3, right? And L3 is this line, which is 3x plus 2y equals to 6. Then solve for y equals to, take this 3x to the right side and divide by 2. It turns out to be y equals to 3 minus 3 half x, and x between 0 to 2. I hope this line or these equations of these lines make sense to you all. Now let's talk about along the line first, means L1. So our fxy, y is 0 along the line first, then fx equals to x squared minus 2x. Now here I put on these functions y equals to 0, so I have x squared minus 2x. Now it's a function of single variable, then we can use our calculus 1 idea. So we just take the regular derivatives, f prime x, it turns out to 2x minus 2, set equals to 0. That gives us x equals to 1. So we found a critical point of restricted functions on L1, which is 1, Then since, this is important, since the extreme values of the restriction of functions on line L1, which is function of x, that is x squared minus 2x, can occur at critical points and at the endpoints of the intervals. The interval's endpoint is 0, 2, right? This is in the L1 line, 0 and 2 x values. These are the endpoints of the intervals. So we have the corresponding extreme values as follows. That means I need to find out the extreme values, or I need to evaluate our restriction function at x equals to 1, and at x equals to 0, and at x equals to 2, which I did here. I use these restricted functions. So which turned out to be f1 is -1. I make the same color here so that you understand here. This one is this critical point, and this 0 and this 2 point are this end point. And the value of f0 is 0, f at 2 is 0. So that means f0 is 0. Again, we found our restricted functions. F at 0 is 0. Also at 2 is 0. And 1 we found, the 1 is here. 1 we found values -1. This one. Great. Now let's use the same idea to find the extreme values of our restricted functions on other two lines, L2 and L3. Great. So now along L2 line was our y-axis, where x is 0. So then this reduces to a function of y only. So then here I put x0, x0, that I have y square only. So we have fy equals to y square. This is a function of single variables. We use calculus on idea. Take the ordinary derivatives with respect to y, set equals to 0, gives us value y equals to 0. Great. And again, let me show you the diagram here. Along this line L2, we found critical point again 0 here, and our endpoints are 0 and 3, right, on that line, for that line L2. Great. So since the extreme values of restriction of f on the line L2, which is y square, can occur at critical points and at the endpoints, so let's find the values of these restriction functions at critical point 0, which turned out to be 0, at left hand point of our interval, which is 0, 0. Now here the values are repeated, and at the another endpoint of our line L2, which is 3, f3 turns out to be 9. Great. So we found the values of f at origin and at 3. Let's move on. Now similarly, let's compute the extreme values of restriction of f on line L3. Our along line L3 here, fxy equals to, our y is 3 minus 3 half x. Let me show you this one again. Here's y is 3 minus 3 half x, right? Okay. So here fxy turns out to be f of x comma 3 minus 3 half x. So this is again a function of x. This is turns out to be, here I'm putting this value on our functions. Our function is here. I put x, I put y equals to 3 minus 3 half x, then it's square, and then minus 2x. Great. I hope you are following me. So let me show you the algebra stuffs here. Then we have these expressions. Foil these middle terms and simplify. It gives us 13 over 4 x square minus 11x plus 9. This is a function of single variables, so you can use our calculus 1 idea. So find the ordinary derivatives. F prime x turns out to be this expression. Set equals to 0, solve for x. So x equals to 22 over 13. So we found this critical point in L3. So 22 over 13 is about 1.7. So that means we found the point somewhere here. Let me show you in the graph also. So here is 1.7 the x value, and the corresponding y values, I think maybe this is 1, maybe half of 1. So here maybe this is 1.7 comma 0.5 approximately. So we found the critical point along the L3 is here, and we need to evaluate our f at this point and at the end point at 3, x equals to 3, and x equals to 0 means y equals to 3. Sorry, x equals to 2 here. Awesome. That's my next step here. Let me scroll down. So now let's evaluate our restriction function at 22/13, which turns out to be -4/13, and evaluate at x equals to 0 and at x equals to 2. At 0 it turns out to be f0 equals to 9, and at 2 it turns out to be 0 again. So now let me summarize all this. Now we finish step 2. Now in step 3, let's compare. I make this nice chart here. So here, this is the critical points, this is the value at critical points, and we are classify this. We have 4 columns here. The first inside T, that critical point, we found 0 0, where the value was 0. That's about critical points value here. I put on the graph also here on my right side. And on the boundary of T, we have 3 lines, L1. So along L1, we found critical point is 1. We found critical point is 1 along L1. And the value turns out to be -1. And at both endpoint on L1, at 0, again is 0. At 2, again 0. This B means boundary point. And along L2, means along this line here, we found critical point. Now these all point are y values here. yc equals to 0. Again we found critical point is 0 on L2. The value was 0. And at the end point, at again this end point here, it's again left hand and the right hand. At 0 is again 0. And at 3 it turns out to be 9. Similarly along L3, this line, we found critical point 22/13. 22/13, which is and corresponding y is 6/13, so which is approximately 1.7, 0.5. So it makes sense to us. This point I hide it there, and we evaluate at 22/13. That means at this point our function value turns out to be -4/13, approximately -0.3, and at the end point at here and here means x equals to 0, x equals to 2, x equals to 0 turns out to be 9. Here it's 9. That's the value again we found along this L2 line also here, along L2 line here also. And at 2 we found 0. So this is a complete summary here. So that means several extreme values repeat. So then by looking this chart, the smallest value is -1, so this is the absolute minimum, which occurs at this point here, -1 at the point 1, 0, and absolute maximum occurs at the end point of along L2 and along L3 at 0, 3. I hope this makes sense to you all. So the conclusion is here. The absolute max is +9 at 0.03. Absolute minimum is -1 at 0.10. Great. Now let's move on. Let's do example 5. This is the shortest distance types questions. So find the shortest distance from the point, given point P, to the plane x plus y minus z equals to 1. Sometimes this, if you rewrite this equations as z equals to x plus y minus 1, then we call this a surface. So I hope this makes sense to you all. So solution. So the idea is we need to first define the distance function, then we need to square the distance function and use SPDT to find the shortest distance, means we are minimizing. So let d be the distance from given point to any arbitrary point q on the plane. Then this is our distance formula, which is x2 minus x1 square plus y2 minus yn square plus z2 minus z1 square under the whole radical. So then this z, I need to put value from here. Z equals to, take this z to the right side, bring 1 to the left side. Z equals to x plus y minus 1. So then 1 cancel, simply x plus y square. Now we have equation star. The idea here, so since any point which minimize d square also minimize d, so it's easier for us to find the derivatives without this radical. So let's square and minimize that d square. So we square here d square, and we FOIL this square and simplify. And let's assume this d square is fxy, then it's easier for us in the notation wise to find the derivatives. I hope this assumption makes sense to you all. Then apply SPDT. So first find the partial derivatives of f with respect to x. First partial derivative with respect to x and with respect to y. Set those equals to 0. Solve for x and y. It gives us xy equals to 4/3, comma negative 2/3. These are the only critical point. Then find second partial derivatives. Find the discriminant value at those critical point, which turns out to 12 positive. Since discriminant is positive and fxx is positive, means absolute minimum occurs, because I have only one critical point, and local minimum occurs means absolute minimum occurs there, right? So the absolute minimum means the shortest distance, right? So absolute minimum is the shortest distance. So by equation star, put x and y values here, then that gives us the shortest distance, which turns out to be, put x equals to 4/3, y equals to minus 2/3. Simplify, it gives us 2 over radical 3, approximately 1.15 unit. Great. I hope this makes sense to you all. Now let's move on. Probably the last example 6. Let's talk about the maximum value problems here. The question is, find the dimensions of a rectangular box of maximum volume such that the sum of the length of its 12 edges is a constant k. So here is the rectangular box. So let's start the solutions. We are finding the dimensions, so let's assume our length is x, width is y, and height is z. Then we know 4x plus 4y plus 4z equals to k. Sum of all 12 edges is k. Then solve for z, so z equals to k over 4 minus x minus y. And the volume of this box is volume equals to length times width times height, that is b equals to x times y times z. Put z equals to this expressions here. So that means we have our volume is a function of x and y, which turns out to be k over 4 xy minus x square y minus xy square. Let me scroll down. That's better. Then the idea, let's again find the partial derivatives of v with respect to x and with respect to y. Set equals to 0 and solve for x and y, which I did here. So I found vx set equals to 0. I have this equation 1. Similarly, I found vy set equals to 0. I have equations 2. Let me remind one more time. When you are taking partial derivatives with respect to x, we keep y constant. Similarly, when you take partial derivative with respect to y, we keep x constant. Two equations, two unknowns. solving equation 1 and 2 gives us both x and y values is k over 12, and put those values back on this expression, then z turns out to be again k over 12. That means this box is a cube now, right? So the box is a cube, then the critical point must give the absolute maximum. Then the max volume will be the absolute maximum. Hence, the required dimensions are all x, y, z value is k over 12. I hope this makes sense to you all. So we finish these sections 14.7. Thank you.